Hey guys, in this lesson we would discuss the last type of rational functions that is required for this course. These types of rational functions contain linear and quadratic expressions in the form of p over q. These could be two types, linear over quadratic or quadratic over linear. Example of linear over quadratic function is if we have a linear function on top and we have a quadratic function as a denominator. And the example of quadratic over linear is we can have quadratic function as a numerator and linear function as a denominator. Now, whenever we are given the function in this form, the first step is to see whether the quadratic expression can be factored or not. So be it this type of question or this type of question, step 1 is to check if the quadratic expression is factorable. The types of questions that would be asked in this type of rational function would be to determine the number of discontinuities. Now let's first understand the meaning of term discontinuities. Discontinuities are any breaks in the graph. So there are 4 types of discontinuities that we are always looking for. One is horizontal asymptote, second is vertical asymptote, third type of discontinuity is called a hole, and fourth type of discontinuity is called oblique asymptote. In the previous lessons we have already covered up horizontal and vertical asymptote type of discontinuities. Now when it comes to linear over quadratic or quadratic over linear type of rational function, we would be able to see oblique asymptote and whole type of discontinuity as well. And let's see what type of questions would contain whole or oblique asymptote. Let's say the first example is we are taking linear over a quadratic function. As we know, this rational function contains a quadratic expression, so we have to first check if this quadratic expression is factorable or not. If it is factorable, then we have to factor it. So the numerator is x minus 2, denominator is, because it's a square minus b square type of expression, so it would be a minus b, a plus b, and we see this is factorable. Now if the expression is factorable, then we have to see whether the numerator or denominator has any common factor that can be cancelled out, and we notice here that x minus 2 is common for both numerator and denominator, so we can cancel these out, and we are left with finally 1 over x plus 2, which is a reciprocal of a linear type of a rational function. So in case we are given a question in this form and we are asked to sketch the graph of this function, we do not start graphing this directly. We first have to convert it to this form and then we graph it. That's why step 1, that is factoring the quadratic expression, is the most important step. Now if you're asked to find all the discontinuities in this question, then how do we figure out the discontinuities is? Always remember, the factor that get cancelled out is the one that is going to give us one discontinuity called whole. Since we got x minus 2 cancelled, therefore this expression is going to give us a whole. Now how to determine what is the whole is, whatever expression cancels out, we put that expression equal to 0 and solve for x. So x is equal to 2 is the whole, and that's our first discontinuity. Second discontinuity would come from the final expression that we have got, and that is this one. We know this is a reciprocal of a linear function, and a reciprocal of a linear function would have a horizontal asymptote at y equal to 0. So this is our second discontinuity. Third discontinuity that we're going to see here is the vertical asymptote, and vertical asymptote is when we put the denominator equal to 0 and solve for x. So denominator is x plus 2 equal to 0. When we solve for x, x is equal to negative 2. So we get vertical asymptote as x equal to negative 2. And we notice that this particular rational function has 3 types of discontinuities. Now, if we are asked to make a graph of this expression, x minus 2 over x squared minus 4, we will not make the graph of this expression. We will be making the graph of this rational function. And steps to make the graph of this rational function we have learned in the reciprocal of linear function. So we can choose any one of the 2 methods, method 1 or method 2. So let's say we are given a grid. We know the horizontal asymptote is y equal to 0. We know the vertical asymptote is x equal to negative 2. The y-intercept would be when we put x equal to 0, so it's going to be 1 over 2. that's a positive half. If we use the first method to make a graph of the reciprocal of x plus 2 function, then we have to first make the graph of x plus 2. We can make it on the same grid using a different color. So let's say we are making a graph of x plus 2 now on the same grid. We know y-intercept is 2 here and slope is 1 over 1, so it's rise over run. So if let's say 3 is here and run is here, this is how the 2 points are going to look like. All we have to do is just connect the 2 points and we would get a line. This is the straight line graph that we would get for x plus 2. We can use this graph or we can use the blue graph to make the white graph that is the reciprocal of the blue graph. Now we notice here x-intercept of the blue graph becomes the vertical asymptote of the white graph. We also have a horizontal asymptote there. This is the negative part of the graph. This is the positive part of the graph. We know the original function and the reciprocal functions, positive and negative interval, stay the same. However, increasing interval becomes decreasing and decreasing becomes increasing. This graph is all the way increasing, so its reciprocal is going to be decreasing like this. However, it will not cross the horizontal and vertical asymptote because they are the discontinuities, and in this section it stays below the x-axis because it's negative. This section it will go above the x-axis because this part of the graph is positive and it is still increasing, but our graph is going to be decreasing like this. So this is how the graph of 1 over x plus 2 function would look like. But we notice that we have already mentioned the horizontal asymptote, we have already mentioned the vertical asymptote. That means they have already been drawn on the grid. However, this hole has not been drawn or is not seen in the graph. X equal to 2 is the hole. That means when the x value is 2, in the reciprocal function, we would see a hole. This is the only difference that this reciprocal of a linear function would show us. That is this extra discontinuity that we have to make on the graph. Now, if you're asked to write down the characteristics of this white graph, then we would write down domain as xer, where x should not be equal to plus 2 because at plus 2 we see a hole, so there is no value that exists for x at 2. And at minus 2, we see a vertical asymptote, so that is also a discontinuity. So x is not equal to plus 2 and minus 2. We can write it like this. Next, we have to write down the range. Range is YER, where y should not be equal to the horizontal asymptote, and that is the 0 value. And y should not be equal to 1 over 4. Where do we get this 1 over 4 from? Is when x is 2, what is the value of y? Because if there is a hole, that means at this hole, neither does the x coordinate exist nor the y coordinate exists. How do we find out the y coordinate is? Because our expression is 1 over x plus 2. We just have to sub in place of x this 2 value, and this gives us 1 over 4. That means this is 1 over 4. So there is a hole at 2, 1 over 4. Therefore, we put 1 over 4 for y not equal to it in range. Positive interval because we see this graph is above x-axis on the right side of the vertical asymptote. So positive interval is negative 2 to positive infinity. On the left side of the vertical asymptote, the graph is under x-axis. So it is negative infinity to negative 2. Because this graph is always decreasing, so decreasing interval is negative infinity to negative 2 and negative 2 to positive infinity. This is how we show the intervals, and in math is written with the help of U sign. So this was an example for linear over quadratic expression. Now let's see if we have a quadratic over linear type of a expression or quadratic over linear type of a function, then how to solve that particular rational function. So if we have x squared minus 4 over x minus 2, we notice we can factor it. So we get x minus 2, x plus 2 divided by x minus 2. These two would get cancelled out. Finally, we are left with x plus 2 expression, which is a linear expression. So the types of discontinuities that we would see in this particular question is a hole because one expression got cancelled out. So whole is seen at x equal to 2. And finally, we are left with a linear expression or a linear function. So we are not going to have any vertical, horizontal, or any oblique asymptote. Therefore, we only have one discontinuity in this particular question, and that is whole at x equal to 2. If you're asked to make this into a graph, then we just make a straight line graph of x plus 2. So if this is 2, this is rise over run. This is how the graph is going to look like with a whole at x equal to 2 value. And that's it. We're done this type of question. If you're asked to write on the characteristics, we'll write on the characteristics mentioning a discontinuity at whole. Let's have a third type of question where we have a quadratic over linear type of expression. And we notice that the numerator is non-factorable. And we also notice one more thing, is that the numerator degree is 1 greater than the denominator degree. Denominator degree is 1, numerator degree is 2. So when the numerator expression's degree is exactly one number greater than the denominator expression's degree, then comes a new discontinuity, and that is called oblique asymptote. So if we are asked to find a discontinuity for this particular question, then we definitely know there is an oblique asymptote here. But how to figure that out is, to find out the oblique asymptote, we have to do long division, where we have to divide the numerator with the denominator. We have the numerator as x squared plus 2x plus 4. Denominator is x minus 1. The method to divide is exactly same as we have learned in lower grades for long division. However, here we just see variables along with numbers as well. Now first is we have to think of what multiplied by x would give us an x square, and we know x when multiplied by itself gives us an x square, so that we'll put here. X times x gives us an x square, so x times x square we would write underneath this x square. However, we notice that this x is not alone. There is a minus 1 attached to this x as well. So when we multiply this x with x and we get an x square, we also multiply the negative 1 with x to get a negative x, or negative 1x, that we would put under the positive 2x because we always put the like terms together. Now in long division, once we multiply, for example, if we have 35 divided by 2, so 2 times 1 is 2, then we subtract the given two values to get the remainder, so 3 minus 2 is 1. Here also we would do the same thing. We would subtract the top expression and the bottom expression. When we subtract the bottom expression from the top expression, the bottom expression signs flip. So this was no sign, means this was positive originally. This is minus, so this will become a plus. X squared minus x squared now gets cancelled out. 2x plus 1x gives us a 3x. Then after that, what we do is we bring this number down. Here also we would bring this number down along with 3x. So we would have 3x plus 4 to work with. What multiplied by x would give us a 3x is a 3, and this is going to be a plus 3. So x multiplied by plus 3 gives us a plus 3x. And as this x is not alone, we would multiply this 3 with minus 1. So minus 1 times 3 is a minus 3. Now when we subtract the expression, signs flip. 3x minus 3x plus 4 plus 3 is 7. Our goal is actually to reduce the terms, and that is the reason we try to cancel these terms out. Now we got this as a remainder, but we do not need the remainder. All we need is the quotient. This is called quotient. So this is our solution that we are looking for, or in terms of discontinuities, this is called the oblique asymptote. So now if you're supposed to write down the types of discontinuities in this particular question is, you would say first discontinuity is oblique asymptote at x plus 3. Whenever we are writing the oblique asymptote, we are writing the entire expression. Second is, we would see a vertical asymptote because there is a denominator, and when we would put that denominator x minus 1 equal to 0, we would be able to get the x value as 1. So there is a vertical asymptote at x equal to 1. However, there is no horizontal asymptote in this case because there is a oblique asymptote. So there will be two discontinuities. in a question like this. And this is how we figure out discontinuities when it comes to rational expressions that contain quadratic and linear expressions as numerator or denominator.